Okay, so on to the next video in the Combinatorics series, this time talking about the pigeonhole principle. So the pigeonhole principle makes the sort of assumption, or it is used to model the situation where, for instance, to give a very physical example, you have some collection of pigeons. Every pigeon must go into some pigeonhole. And if you imagine that you have more pigeons than you have holes, then some two pigeons must share a hole. That is the pigeonhole principle. It can be nice to see the somewhat more mathy version of the same thing and generalized a little bit. So here we have a function from a domain, which is like your set of pigeons, to your range, which is like the set of pigeonholes. Each of these we will imagine are finite sets, and we suppose that the size of the domain is strictly greater than a multiple of n, right? So k is a multiplier, the range will have size n, and so if we imagine that we have more than k times n in the domain, then some element in the range, again, right, some pigeonhole, so to speak, has more than k pigeons in it, right? That is to say, there is the pre-image is the set of all pigeons that go to that pigeonhole, and so we're saying that more than k pigeons go to that pigeonhole. There is also what is sometimes called a statistical pigeonhole principle, which has a similar feel to the pigeonhole principle. If you have a non-empty set of real numbers, let us denote a bar the mean, then this principle tells us that the max of the set of real numbers, the greatest of those real numbers, is greater than or equal to the average, which is sort of intuitively true. The book presents this as, I believe it presents it as an equivalent principle. I cannot think of any proof of the statistical pigeonhole principle using the regular pigeonhole principle. So I can certainly, there are relatively easy proofs of each of these principles, but I cannot see how to make an essential use of the pigeonhole principle to prove this statistical pigeonhole principle. So in that sense, I'm not sure how they're equivalent, but certainly both principles are true. Anyway, and they have a similar feeling to them, right? That numbers are getting kind of trapped in a region. But anyway, that's just a brief introduction to the various pigeonhole principles.